Hi, everyone. Welcome back to 2.2. So we established the coordinate plane and some interesting things about any 2 points, right? We found some distances between points. We found some midpoints between points. And what we're going to do is now graph equations. Now, graphing equations itself isn't a crazy process, but there are some very interesting things that come out of graphing. So let's just look at some basics. Well, think about when we were solving equations in chapter 1. If we plugged in some answer from our solution set, if the equation held true, then we would have, we would say that thing is a solution. Well, here in chapter 2, when we're looking at things in 2 dimensions, we now not only have a single x equals or x is greater than something, what we now have is a point that we're plugging in. So no more just x equals and plugging in things for x. What we're now going to be doing is plugging in x's and y's. So we say the coordinate point AB is a solution if it satisfies an equation when plugged in. So for example, the equation y equals x squared plus 1 has a solution 2, 5. Because if we plug in 2 for x and 5 for y, well, we get 5 equals 2 squared plus 1. We know 2 squared is 4, and 4 plus 1 is 5. This equation's true, so this is a solution. However, 3, 7 wouldn't be a solution because when we plug in 3 in for x and 7 in for y, then 3 squared is 9, 9 plus 1 is 10, and 7 doesn't equal 10. So in the graph of y equals x squared plus 1, 2, 5 will be one of the points that's included, but 3, 7 will not be. So the graph of an equation in general is actually a collection of solutions. We rarely ever think about it that way. We kind of think about them as individual points that we connect. But in all actuality, the graph of an equation is actually all the solutions associated with that equation. So just some terminology here. If y is found by plugging in x, then we say y is the dependent variable and x is the independent variable. Or in other words, what we're doing in most cases, plug in x to get some y. All right, easiest way to graph is to make what we call a table of values. And in general, maybe like plugging in values from -3 to 3 might be helpful, but that isn't going to be always your only option. So we're going to begin with a set of x values and plug them in to find corresponding y values. Well, if we plug in x's and we get y's, we have a bunch of coordinate points, x, y's, or ab's. We're going to plot those points and then connect them. So let's say we have y equals x squared minus 3. Well, this is what your table could look like. And we're going to plug in some arbitrary x's that we want to plot. Like I said, in general, -3 to 3 isn't a horrible option, but depending on what your equation is, depending on what values are allowed, what values are easy to calculate, you might want to choose some other set of values besides just -3 to 3. Again, I'm using -3 to 3. That doesn't need to be your only option. Well, if x is -3, we're going to plug in -3. -3 squared is 9. 9 minus 3 is 6. So that means one of the solutions to this equation is -3, 6. And -3, 6 will be on the graph of y equals x squared minus 3. Let's do -2. Well, we're going to plug in -2 for x. -2 squared is 4. 4 minus 3 is 1. So the point -2, 1 is on the graph of our equation. Let's do -1. -1 squared is 1. 1 minus 3 is -2. So -1, -2 is a point. And I think you guys get the idea here. But take a second, look at all the points that we have. Okay. Now, you might notice there's some funky things about the y values and the x values, but don't think about those right now. Don't worry too much. We're going to come back to that by the end of the section. Okay, so let's take all 7 of these coordinate points and plot them. That's the first thing we did in 2.1. So all of those points are right here. And what we're going to do is connect them with a nice, smooth curve. Now, how did we know it looks like that and maybe not a little bit more jagged? Well, it comes with practice, comes with understanding what x squared looks like. It's a parabola. We haven't really defined what parabolas are, but there we go. Look for the pattern of what your graph will look like. If you can't quite figure out a pattern, graph more points. The more points you have, the easier it is to figure out what your graph is going to look like. Let's do one more. Y equals absolute value of 2x minus 4. Okay, let's plug in -3 for x. 2 times -3 is -6. -6 minus 4 is -10. Absolute value of -10 is +10. So that means we have a point at -3, 10. Let's plug in -2. 2 times -2 is -4. -4 minus 4 is -8. Absolute value of -8 is +8. Please be careful. Don't use absolute values too early. Simplify the inside before you take absolute value of anything. So we have -28 as a point. -1, 2 times -1 is -2. -2 minus 4 is -6. Absolute value of -6 is +6. So we have -1/6. All right, at 0, 2 times 0 is 0. 0 minus 4 is -4. Absolute value of -4 is 4. Okay. What else when we plug in 1? In the last example, value started to repeat. Are they going to do that here? Is it going to be nice, perfectly symmetrical? Keyword symmetrical here. Well, when we plug in 1, 2 times 1 is +2. +2 minus 4 is -2. -2, absolute value of that is +2. Oh, yeah, you might be able to find patterns, but don't be too quick to jump the gun, so to speak, and look for them, right? See them as they come. And if you don't see them, that's okay. You'll get better at it. All right, if we plug in 2, 2 times 2 is 4. 4 minus 4 is 0. Absolute value of 0 is 0. 2, 0. And do one more. 2 times 3 is 6. 6 minus 4 is 2. Absolute value of 2 is 2. So 3, 2 is a point. So let's plot all those points. And we actually kind of get like a check mark type of thing right here. So maybe you don't see it right away. And if you're looking at this going, I'm not really sure what's going to happen after 3, that's okay. Just plug in more points. It's not going to hurt you. If you were to plug in 4, you would have had 2 times 4 is 8. 8 minus 4 is 4. Absolute value of 4 is 4. So it's okay to plug in more points than necessary. And like I said, maybe -3 to 3 isn't the ultimate option. Maybe you want to do -2 to 5 or -3 to 6, right? Whatever works for you to figure out what the graph looks like, by all means, do it that way. Okay, well, that brings us to something called intercepts. And you've been wondering, why do we solve equations? We haven't solved a single equation so far in this chapter, and here we go. So intercepts are points that cross the x or y axes, or they intercept the x or y axes. So the y-intercept, I just want to go back to our graph here real fast. The y-intercept would be the point that crosses the y-axis. But let me ask you something. Ignoring the graph right here, what do all of the points that would be y-intercepts have in common? This is a y-intercept, this is a y-intercept, this is a y-intercept, this is, right? What do all of these points have in common? Well, I'll tell you since we're not talking directly, but all of them have the same x value. They all have the same x value of 0. So if you want to find the y-intercept, if you want to find where it crosses this line, set x equal to 0. And likewise, x-intercepts, we'll find that in just a second. Well, if we want the x-intercepts, we would set y equal to 0. All of these points that I'm covering with my cursor right now, well, all of them share the same y value, y equals 0. Okay, so y-intercept, you set x equal to 0 and solve for y. Then you would say 0, comma, whatever that y is your y-intercept. X-intercepts, we're going to set y to 0 and solve for x. And x comma 0 are going to be the x-intercepts. Now, you might be wondering why I'm not using y-intercepts, plural, but I'm using it for x-intercepts. Essentially, it comes down to the definition of a function in 2.4. And when we get there, we're going to say that we're not allowed to have multiple y-intercepts. But for now, it's more likely than not you're just going to have a single y-intercept. Okay, so let's find the intercepts of 12x plus 14y equals 16. If I want the y-intercept, we're going to set x equal to 0. So instead of 12x plus 14y equals 16, this is going to be 12 times 0 plus 14y equals 16. Well, 12 times 0 is just 0. 14y equals 16. We're going to divide both sides by 14. And then 16 over 14 is 8 over 7. So the point 0, comma 8 over 7 is the y-intercept. X-intercept, let's set y equal to 0. So 12x plus 14 times 0 equals 16. 12x equals 16. Divide both sides by 12. 16 over 12 is 4/3, but for x-intercepts, it would be 4/3, comma 0. So there is 0, comma, what was it? 0, comma 8 over 7, 4/3, comma 0. And actually, interestingly, when it comes to lines, if you know the x and y intercepts, you can graph them. This is only true for lines, though. We haven't really described what lines are. We'll do that in 2.3. All right, let's find the intercepts of y equals x squared minus x minus 2. Let's solve for the y-intercept first. Let's set x equal to 0. Well, 0 squared minus 0. 0 squared is 0, minus 0 is 0, minus 2 is negative 2. So 0, comma negative 2 is the y-intercept. Now we're actually going to get multiple x-intercepts here, and this is where solving equations became a big deal to us, especially in 1.3. We're going to set y equal to 0, but notice this is a quadratic equation. This is something that you would use quadratic formula for, completing the square, or even easiest, factoring. Set each factor equal to 0. X minus 2 equals 0, you would get 2. X plus 1 equals 0, you would get negative 1. So negative 1, 2 are the x-intercepts, but formally written as points, negative 1, 0, comma 2, 0. So you wouldn't be able to graph this just with those 3 points. You could if you're very careful about what you're doing, but odds are don't try and do what we just did for lines in the last example. Okay, another one. Find the intercepts of x cubed minus 9x. Y-intercept, set x equal to 0. Well, this is pretty nice. 0 cubed is 9. 9 times 0 is, 0 cubed is 0. 9 times 0 is 0. 0 minus 0 is just 0. All right, cool, nice. 0, 0 is our y-intercept. X-intercepts, we're going to set y equal to 0. So let's factor out x to solve this. X squared minus 9 is x plus 3x minus 3. And then set each of these 3 factors equal to 0. X equals 0 at just 0. X minus 3 equals 0 at 3. X plus 3 equals 0 at negative 3. All right, well, we have 3 x-intercepts. That's okay, totally fine. Okay, and what you might also notice is that the y-intercept and x-intercepts are the same, or not entirely the same. There's 2 more x-intercepts than there are y-intercept, but it's okay that the x and y-intercept match, that we repeat. That's totally fine. It just means it crosses the x and y axis at the same time. Okay, find the intercepts of x squared plus 9, square root of x squared plus 9. Y-intercept, set x equal to 0. Okay, well, 0 squared is 0. 0 plus 9 is 9. Square root of 9 is 3. So 0, comma 3 is our y-intercept. Let's do the same for x-intercept. Let's set x equal to 0, or sorry, let's set y equal to 0. Well, let's square both sides. Let's subtract 9 on both sides. And, well, we could take the square root of both sides, but we would get x equals plus and minus 3i. And we've never graphed I before. Or even easier, there's just no solution here. And that's okay. You don't always need an intercept of some type. It's okay to get no x-intercepts or no y-intercept. It entirely depends on the graph. One thing I'll also note is, we spent a decent amount of time in all of 1.4 talking about I and complex numbers, but at no point did we talk about graphing complex numbers. So almost everything we do here in chapter 2 will be entirely based upon real numbers. So don't worry about I so much when it comes to graphing. Okay, intercepts of y equals square root of x minus 9. Y-intercept, set x equal to 0. 0 minus 9 is negative 9, and we can't take the square root of negative 9. So same thing here. There just is no y-intercept. That's totally fine. X-intercept, however, let's set y equal to 0. Let's square both sides. Let's add 9 to both sides. So we get 9 comma 0 is our x-intercept. So like I said, not necessarily a rhyme or reason as to when we get x-intercepts versus y-intercepts, and that's totally okay. But now let's talk about symmetry, right? The very first example we talked about when we were making a table of values, it was symmetric over the y-axis. It was perfect on both sides of the y-axis. It matched. Well, there's a specific property of that called symmetry. So they might have symmetry about certain lines or points, and we're going to talk about symmetry again once we get to 2.4, I think, or 2.5. So graphs have symmetry over certain lines or points, like the x or y axes and the origin. Well, we can algebraically determine if something is symmetric. We don't need to try and graph something we don't really know how it looks. So to algebraically determine if something is symmetric, we're going to do one of the following things. If we are testing for symmetry over the y-axis, we are going to replace every x with negative x and simplify. Okay, now you might be wondering why symmetry over the y-axis would change x. Well, think about it this way. Here, we had a parabola before where it was symmetric over the y-axis. Now, the y values were the same on the different parts of the symmetry. The only thing that was different were the x values, right? This would have been like x is negative 3. This would have been like x is positive 3. So if we want to check for symmetry over the y-axis, we replace x with negative x. You could also think about it as like solving for y-intercepts. Y-intercepts, we set x to 0, symmetry over the y-axis, replace x with negative x, and then simplify. For symmetry over the x-axis, well, you probably guessed it, we're going to replace every y with negative y. And then for symmetry over the origin, this is kind of weird. Long story short, replace both x with negative x and y with negative y and simplify. Okay, so in all of these cases, you simplify, and if the simplified equation is exactly like the original, exactly the same as the original, then it is symmetric about that axis or point. If it is not identical to where you started, it is not symmetrical over that axis or point at which you are testing. So again, just to summarize, symmetry over the y-axis, replace x with negative x and simplify. If they're equal, symmetric. And you see the cases for x-axis and origin. Okay, so is 1 over x squared plus 5 symmetric over the y-axis? Okay, symmetry over the y-axis, we're going to replace x with negative x. Okay, so we have y equals 1 over x squared plus 5. Replace x with negative x. And here's what I mean by simplifying. Negative x squared is the same as positive x squared. Okay, and now no more simplification we need to do. So now the question is this new equation exactly the same as the original? Well, you see that this starting point, this ending point are identical. So that means we are symmetric about the y-axis. Cool. Well, there's the graph of 1 over x squared plus 5. Not the prettiest thing in the world, but you see that it is symmetric over the y-axis. 4x minus x cubed, is this symmetric over the y-axis? Well, symmetry over the y-axis, we're going to replace x with negative x. So wherever we see x, write negative x. So instead of 4 times x, it's going to be 4 times negative x. Instead of negative x cubed, it's going to be negative x cubed. All right, well, 4 times negative x is negative 4x. Negative x cubed itself is negative x cubed, but negative x cubed is positive x cubed. Okay, no more simplification we can do, but now is this equation that we started with identical to the equation that we ended with? The answer is no. So this is not symmetric about the y-axis. Okay. Well, you probably noticed there was something in common with that last example. There's something weird about that example. Why don't we test it over the origin? For symmetry over the origin, replace both x with negative x and y with negative y. Alrighty, so wherever we see x, we're going to write negative x just like the last one. And wherever we see y, we're going to write negative y just like, or not just like, similar to what we've already been doing. Okay, well, we just simplified the right-hand side before, but we have negative y, and we want to eventually get it to look like y equals to be able to compare them. So why don't we divide everything by -1? Divide everything by -1 because negative y divided by -1 is now positive y. Negative 4x divided by -1 is positive 4x. Positive x cubed divided by -1 is negative x cubed. And now my question is, are these identical? And sure enough, they are. So it is symmetric about the origin. Okay. Very last thing here in 2.2, we're going to talk about graphing circles. This is going to be likely the only time we talk about circles in the entire course. So buckle up. It's not that scary. So with the help of SpongeBob, we're not talking about this or this. We are talking about circles, of course. Krusty Love from 2002, legendary episode. SpongeBob helps Mr. Krabs go on a date with Mrs. Puff. Very big deal. Okay, the formal definition of a circle is, if I ask you to define it, you're kind of like, well, I don't know. It's like this, right? It's this kind of thing. The formal definition is kind of clever, if you're not really thinking in that way, but it's a set of points that are all a fixed distance away from a center. So we have some center, all the points that are, say, 5 units away from that center. So kind of a weird way of thinking about it, but it is very true and it makes a lot of sense. That fixed distance away from the center we refer to as the radius, which we denote with the letter r. And the center is denoted by the point h, comma, k. So here's a good example of why we're not always trying to reuse the same letters over and over again. A, B, a little different, but HK would be the center of the point. Now, standard form of a circle looks like this. And this is where things are a little strange. Well, this says x minus h squared plus y minus k squared equals r squared. Well, r squared, we can take that for granted. That's not so bad. But you might be wondering why we have x minus h. Well, be very careful. Okay, if our center has positive points, let's say 3, 2. Well, if h is 3, then you plug in 3 here, and you would have x minus 3. If k was 2, you would have y minus 2. So the signs of your center in the equation are going to be backwards. If the center is positive, that part of the equation is going to be negative. So be very careful about that. So let's write the equation of a circle with a center 4, 2 and a radius 7. Well, hk would be 4, 2. So h would be 4, k would be 2, and your radius is 7. Okay, that's given to us. That's not so bad. Well, let's start with this equation right here. And again, h right away is 4 and k is 2. Radius is 7. And now you might be a little uncomfortable that like, oh, well, our center is positive, but these are negative. Yes, that is on purpose. Please be very careful. I'm aware this is positive and these are negative. That is by design. Okay, so there's nothing to change here, but we do know that 7 squared is positive 49. Okay, so this would be the equation of a circle whose center is at positive 4, positive 2 with a radius of 7. Let's do the same thing, but for negative 6, 3. Well, hk is negative 6, 3. So h is negative 6, k is 3. The radius is 1. So again, when we go to plug these things in, just be very careful. H is negative 6, k is 3. and radius is 1. Well, here, now we see the difference between positive center values and negative center values. X minus negative 6 is positive 6. Y minus 3 doesn't change, and 1 squared is just 1. So again, there is an element of like kind of flipping signs here, sort of. So be very careful with the signs of your center in or coming from an equation. Okay, let's do one more example of writing equations. Center is negative 5, 9, and the radius is square root of 14. HK would be negative 5, negative 9. So H is negative 5, and K is negative 9. Radius is square root of 14. That's given to us. Okay, well, X minus H plus Y minus K squared equals R squared. H is negative 5. K is negative 9. And R is square root of 14. But here we're going to get plus plus. Here we're going to get plus plus. And square root of 14 squared is just 14. So again, I can't stress enough, be careful with centers of circles. Well, what if we want to go backwards? Alrighty, well, x minus 6 squared plus y minus 7 squared equals 100. The center is always h comma k. So in this case, it would be 6, 7. Don't forget, negative 6 is going to mean positive 6. Negative 7 is going to mean positive 7. Now the radius, well, in the circle equation, it's x minus h squared plus y minus k squared equals r squared. So r isn't 100. R squared is 100, which means that r is 10. So, technically, you take the square root of both sides, you get r equals plus and minus 10. Kind of like hypotenuse in 2.1, it doesn't make sense to talk about, negative distance. So radius is 10. X plus 7 squared plus y plus 6 squared equals 25. Well, center is going to be backwards values, right? X minus h. This is x plus 7. So our center is going to be negative 7 and negative 6. Radius, well, r squared is 25, so r is 5. Okay, again, be careful with signs. X squared plus y squared equals 1. Well, there's nothing adding or subtracting x, so center is just 0, 0. Okay, well, radius, r squared is 1, but that also just means that r is 1. So, we could also have written our circle like this: x minus 0 squared plus y minus 0 squared equals 1. And now you kind of see a little bit more as to why the center is 0, 0. Also, this is the equation of what is called the unit circle in pre-calc. So you might see this equation again in the future. X minus 10 squared plus y plus 10 squared equals 12. Well, center, alrighty, x minus h. So h is positive. X minus h, h is 10. Y minus k, oh, but k is going to be negative, right? Opposite signs. So the radius, well, r squared is 12, which means that r is square root of 12. So be careful of that as well. Let's say we wanted to graph. Well, let's do exactly what we were just doing. Extract all of the information about the circle and then go to graph it. Well, our center will be negative 2, comma, positive 3. The radius, well, r squared is 25, so r is 5. So what we're going to do is start from the center, negative 2, 3, and go out 5 units. The radius, 5 units in each direction. So let's plot the center, negative 2, 3. Let's go 5 units up, 5 units to the right, 5 units down, and 5 units to the left, and connect those points. And that's how we get a circle. Okay, let's do it one more time. X minus 5 squared plus y plus 1 squared equals 9. Well, our center is going to be positive 5, negative 1. Well, r squared is 9, so r is 3. Okay, so start at the center and now move 3 units in every direction. There's 5 comma negative 1. go up 3, go right 3, go down 3, go left 3, and connect those points. And that's how we graph circles. Not the scariest thing on the planet, I don't think. Okay, so that's 2.2. We are slowly working our way to functions. So we've now done what the plane is, graphs of any equation, and what we're going to do in the next section are lines. Okay, so with that said, I will see you in 2.3. Bye.
Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Leswowska Zerpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.